Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to sensors and transducers, and we'll extend our discussion on the use of magnetostrictive transducers for measurement of various physical parameters. So in this video we are going to discuss how we can use it to measure displacement in various arrangements in various ways. So again, first we'll have a quick review of magnetostrictive effect. We have discussed it a lot in the previous videos, but just to go in a systematic way, magnetostrictive effect is the basic property of ferromagnetic magnetostrictive materials, in which when they are exposed to a fluctuating magnetic field, changing magnetic field, that causes change in their shape or dimensions. Now it is because of the ferromagnetic magnetostrictive materials which have a lot of dipoles, magnetic dipoles, which are clustered together, grouped together, called as domains. So when they are exposed to a magnetic field, the direction of the dipoles, they are aligned in the direction of the changing magnetic field. So that's why it causes a change in the shape or size. So this is the magnetostrictive effect, where change in magnetic field on the input side causes a change in the shape on the output side. That is the cause and effect relationship. The reverse is called as the Villari effect, the reverse magnetostrictive effect, which is the opposite. That is, when a force or pressure or stress is applied on the magnetostrictive material, it responds with a change in its magnetic characteristics, such as permeability, susceptibility, etc. So here the cause is application of force or pressure or stress. The effect is change in permeability, susceptibility, or other magnetic characteristics. We are particularly interested in this relative permeability thing. Now the basic design of any magnetostrictive sensor is with respect to the design consideration. It is in the form of a solenoid or toroid, which is a ferromagnetic material with number of turns of wire wound over it, with current supplied, generally constant current is supplied, fixed number of turns, and it obeys this relationship, where the magnetic flux density is given by this mu 0 mu r n I. Mu 0 is the absolute permeability, mu r is relative permeability, n is the number of turns of wire, I is the current. Here current is fixed, it is kept constant, then number of turns of wire, that is fixed, absolute permeability is fixed. So the only thing that is variable here, changing here, is this relative permeability. So this relative permeability, it causes a change in the magnetic flux density. This is the basic principle which is utilized, because we want to get an electrical output, voltage or current. So how it produces that? Let's see. Everything else is constant, mu 0 n I. Mu r changes with respect to application of force, pressure, stress, whatever it is. That causes a change in relative permeability. Relative permeability causes a change in magnetic flux density. Now magnetic flux density, as it changes, it causes a change in magnetic flux, which is the dot product of the magnetic field vector and the area of the coil, okay, the solenoid or toroid coil. So this angle is kept constant, it is fixed. So the only thing that responds here, the magnetic flux, the area of the coil is constant, the angle of orientation is constant. So the only thing that is changing is this magnetic flux. This magnetic flux density is changing with respect to relative permeability. Relative permeability causes a change in magnetic flux density. Magnetic flux density causes a change in magnetic flux, phi v. So as magnetic flux changes, it induces an EMF as per Faraday's law of electromagnetic induction, which is given by this n d phi b by dt, rate of change of magnetic flux. Here we are not considering the negative sign as per Lenz's law, because we are only interested in the magnitude. Well, in some cases the direction of the EMF induced is also important, but for now just focus on this. Okay, so here this is the sequence of events. Relative permeability causes a change in magnetic flux density. Magnetic flux density causes a change in magnetic flux. Change in magnetic flux produces an EMF, and these all things are constant here. They are all constant. Okay, so how we can use it for measurement of displacement? So this is the basic design of a magnetostrictive sensor, where we have the toroid or solenoid material placed on a platform. Then we have a material which kind of channelizes the whole impact towards the toroid or solenoid, and this is the point of impact. So this can be arranged in different ways. This is one arrangement where, suppose there is a moving object which has to be, its motion has to be detected. It is placed in line with the magnetostrictive sensor. It is placed in its line of action. So when it moves and it strikes this magnetostrictive sensor, it gets activated. That's one way. Another way is, if two-way motion has to be detected, then another magnetostrictive sensor is placed here. So if there is to and fro movement like this way and this way, both sides the sensor will be activated. Another magnetostrictive sensor is placed in the left side also. So both sides it gets activated when it crosses a certain point. Okay, this is one way of measuring displacement. They are placed at fixed distances from the center point, kind of a SHM motion, simple harmonic to and fro motion. This is one way. Another way is, suppose we want to measure we want to continuously monitor the position of the object and how much distance it has traveled. So in that case, what is done? A series of magnetostrictive sensors is placed at fixed distances. Let's say along the x-axis. Let's say this is x is equal to 0 meter, another is placed at x is equal to, let's say, 4 meter, another is placed at x is equal to 8 meter. So as this object moves, as it here the sensor gets activated when it reaches this position. When it moves, when it makes any movement, the sensor is activated. Then it goes, when it reaches here, it strikes this sensor, then again here it is activated. So we get a signal that the object is currently at this position and has covered total of 4 meters. Then as it reaches here, again this sensor is activated. So the current position is at x is equal to 8 meter. Total distance traveled is, or displacement is, 8 meters. So like that kind of arrangement is also there. This is linear displacement or linear tracking. Then if we want to measure angular motion or angular displacement, then it can be like this. Okay, so where we have a circular design where the sensors are placed at different angles. This is first it is at 0 degree angle. Okay, theta is equal to 0 degree angle, then theta at 90 degree angle, then theta at sensor is placed at 180 degree, then 270 degree, and then again 360 degree or 0 degree, like this. This is one way where as this thing rotates, first it is at this position, it strikes, so the object is at 0 degree. Then as it strikes here, the object is at 270 degree position, then at 180 degree, and again at 90 degree. And if we want more precise and more measurements, more data, then we can also put sensors at in between positions, between these two positions. Okay, 0 degree, then 45 degree, then 135 degree. Okay, like this, 180 degree, then this is 180 degree plus 225 degree, then 270, then how much, 315 degree. Like this also we can place sensors. Then also we can measure at every 10 degree, 20 degree, 30 degree, like that also. If we want recordings, if we want data related to that, also we can put sensors accordingly. So one thing has to be taken into consideration: the more the number of sensors, the more the cost, the more the maintenance cost, the more the circuitry which will be required to process the signals. So everything will be just get magnified. So depending upon the operational requirements, we can place sensors accordingly. So this is for angular motion tracking, okay, and this is linear motion tracking, and this one is to and fro motion, okay, to and fro motion. And there can be other arrangements also. These are the simple arrangements for measurement of displacement. Okay, so this is the basic relationship. So what happens is that whenever the object strikes the sensor, it the sensor gets stressed. As it gets stressed, its relative permeability changes. Relative permeability causes a change in magnetic flux density. Magnetic flux density causes a change in magnetic flux. Magnetic flux change causes an EMF generation. Okay, this is the basic relationship, and this is the final relationship between stress and EMF, which is given by Et is equal to San d sigma t by dt, where E is the time varying EMF which is generated, S is the sensitivity of the sensor, A is the coil area, N is the number of turns, and d sigma t by dt is the time varying stress which is applied. Okay, so this is the the simplest use of magnetostrictive sensors for measurement of displacement in various arrangements. Okay, so let us try to understand this whole thing from a three-dimensional point of view. So as I said, this is the to and fro displacement measurement. So suppose this object, it has to and fro movement like this, and it strikes this magnetostrictive sensor here. So as it strikes, this sensor gets activated and it produces the signal. The same thing can be done in reverse also, where this sensor can be placed here in the opposite direction here, okay, like this. Another sensor is placed here. So as it strikes in this direction also, the sensor gets activated. So here the thing is that this object is placed at a fixed distance apart from both of these two magnetostrictive transducers. Okay, this is the to and fro motion detection. The next arrangement is this, the linear motion arrangement. So here the object moves in a straight line path in a particular direction. So as it is currently in this position, this sensor gets activated. As the object moves, it reaches this position again. This sensor gets activated, then it gets triggered and the signal is transmitted, and then as it finally reaches this position, this sensor gets activated. So here the thing is that the sensors are placed at fixed distances. Separation distance between each sensor is same. So suppose here it is x is equal to 0 meter, then it would be placed at x is equal to, let's say, 4 meter, x is equal to 4 meter, then in this case it is x is equal to 8 meter, so like that. Or depending upon the requirement, where at specific positions, if you want to detect the motion, depending upon that also the values and position of the placement of the sensors can change. It depends on the operational requirement. Then the third one is the rotational displacement, which is this is the rotating component. So as it rotates and moves to different position, accordingly different sensors are activated. In this position, okay, then it rotates here, at 90 degree, then this sensor gets activated, and likewise the different sensors are activated. Now if we want more precise measurements, then depending upon that, different locations where we want to place the sensors, they can be done. Okay, like if you want it here, then we can place another sensor here. Okay, we can place another sensor here. Okay, then another sensor. Okay, we can place another sensor here, then another sensor here. Accordingly, we can place it at different points. Okay, like this, for more accurate and precise measurements. Okay, so at different as this rotating component reaches different positions, when it rotates, the sensors at different positions get triggered and they give us the values. As it rotates throughout like this, at the center, the sensors at different positions get triggered. Okay, like this. Okay, so this is another arrangement. Okay.